In this lesson, you'll step through the entire training process and at the end, see the model improve on your task, specifically for you to be able to chat with it. All right, let's jump into it. All right, training an LLM, what does this look like? So the training process is actually quite similar to other neural networks. So as you can see here, the same setup that we had seen the LLM predict, SD, ! At. What's going on? Well, first you add that training data up at the top, then you calculate the loss, so it predicts something totally off in the beginning, predict the loss compared to the actual response it was supposed to give, that's a pawn. And then you update the weights, you backprop through the model to update the model to improve it such that in the end it does learn to then output something like a pawn. There are a lot of different hyperparameters that go into training LLMs. We won't go through them very specifically, but across a few that you might want to play with is learning rate scheduler, and various optimizer hyperparameters as well. All right, so now diving a level deeper into the code. So these are just general chunks of training process code in PyTorch. So first you want to go over the number of epochs. An epoch is a pass over your entire data set. So you might go over your entire data set multiple times. And then you want to load it up in batches. So that is those different batches that you saw when you're tokenizing data. So that's sets of data together. And then you put the batch through your model to get outputs. You compute the loss from your model and you take a backward step and you update your optimizer. Okay, so now that you've gone through every step of this low-level code in PyTorch, we're actually going to go one level higher into Hugging Face and also another level higher into the Llama library by Llama just to see how the training process works in practice in the lab. So let's take a look at that. Okay, so first up is seeing how the training process has been simplified over time quite a bit with higher and higher level interfaces. That PyTorch code you saw, man, I remember running that during my PhD. Now there are so many great libraries out there to make this very easy. One of them is the Llama library, and it's just training your model in 3 lines of code that's hosted on an external GPU, and it can run any open source model and you can get the model back. And as you can see here, it's just requesting that 410 million parameter model. You can load that data from that same JSON lines file, and then you just hit model.train. Cool, and that returns a dashboard, a playground interface, and a model ID that you can then call and continue training or run with for inference. All right, so for the rest of this lab, we're actually going to focus on using the Pythia 70 million model. You might be wondering why we've been playing with that really small, tiny model, and the reason is that it can run on CPU nicely here for this lab so that you can actually see the whole training process go. But realistically, for your actual use cases, I recommend starting with something a bit larger, maybe something around 1 billion parameters, or maybe even this 400 million one if your task is on the easier side. Cool, so first up, I'm going to load up all of these libraries. And one of them is a utilities file with a bunch of different functions in there. Some of them that we've already written together on the tokenizer, and others you should take a look at for just logging and showing outputs. So first, let's start with different configuration parameters for training. So there are 2 ways to actually import data. You've already seen those 2 ways. So one is just not using Hugging Face necessarily. You just specify a certain dataset path. Another one, you could specify a Hugging Face path, and I'm using a Boolean value. Use Hugging Face to specify whether that's true. We include both for you here, so you can easily use it. Again, we're going to use this smaller model so that it runs on CPU. So this is just 70 million parameters here. And then finally, I'm going to put all of this into a training config, which will be then passed onto the model just to understand, what the model name is and the data is. Great, so the next step is the tokenizer. You've already done this in the past lab, but here again, you are loading that tokenizer and then splitting your data. So here's just the training and test set, and this is loading it up from Hugging Face. Next, just loading up the model. You already specified the model name above, so that's 70 million parameter Pythia model. I'm just gonna specify that as the base model, which hasn't been trained yet. Next, an important piece of code, if you're using a GPU, this is PyTorch code that will be able to count how many CUDA devices, basically how many GPUs you have. And depending on that, if you have more than 0 of them, that means you have a GPU, so you can actually put the model on GPU, otherwise it'll be CPU. In this case, we're going to be using CPU. You can see select CPU device. All right, so just to put the model on that GPU or CPU, you just have to do the model to device, so very simple. So now this is printing out the, what the model looks like here, but it's putting it on that device. All right, so putting together steps from the previous lab, but also adding in some new steps is inference. So you've already seen this function before, but now stepping through exactly what's going on. So first you're tokenizing that text coming in. You're also passing in your model, so that's the model here, and you want the model to generate based on those tokens. Now, the tokens have to be put onto the same device so that, if the model is on GPU, for example, you need to put the tokens on GPU as well so the model can actually see it. And then next, there's an important, max input tokens and max output tokens here as parameters for specifying, how many tokens can actually be put into the model as input, and then how many do you expect out. We're setting this to 100 here as the default, but feel free to play with this, make it longer so it generates more. Note that it does take time to generate more, so expect a difference in the time it takes to generate. Next, the model does generate some tokens out, and so all you have to do is decode it with that tokenizer, just like you saw before. And here, after you decode it, you just have to strip out the prompt initially because it's just outputting both the prompt with your generated output. And so I'm just having that return that generated text answer. So great, this function you're going to be using a lot. So first up is taking a look at that first test set question and putting it through the model. And try not to be too harsh, and I know you've already kind of seen this before. So again, the model is answering this really weird way that you've seen before. It's not really answering the question, which is here, and the correct answer is here. Okay, so this is what training is for. So next, you're going to look at the training arguments. So there are a lot of different arguments. First, key in on a few. So the first one is the max number of steps that you can run on the model. So this is just max number of training steps. We're going to set that to 3 just to make it very simple, just to walk through 3 different steps. What is a step exactly? A step is a batch of training data. And so if your batch size is 1, it's just 1 data point. If your batch size is 2,000, it's 2,000 data points. Next is the trained model name. So what do you want to call it? So here I'm calling it the name of a data set plus the max steps here so that we can differentiate it if you want to play with different max steps and the word steps. Something I also think is the best practice that's not necessarily shown here is also to put the timestamp on the trained model because you might be experimenting with a lot of them. Okay, cool. So I'm now going to show you a big list of different training arguments. There are a lot of good defaults here, and I think the ones to focus on is max steps. This is probably going to stop the model from running past those 3 steps that you specified up there, and then also the learning rate. There are a bunch of different arguments here. I recommend that you can dive deeper into this if you're curious and be able to play with a lot of these arguments, but here we're largely setting these as good defaults for you. Next, we've included a function that calculates the number of floating point operations for the model, and so that's just flops and understanding the memory footprint of this base model. So here it's just going to print that out here. This is just for your knowledge, just to understand what's going on, and we'll be printing that throughout training. And I know we said that this was a tiny, tiny model, but even here, look how big this model is here with 300 megabytes. So you can imagine a really large model to take up a ton of memory. And this is why we need really high performing large memory GPUs to be able to run those larger models. Next, you load this up in the trainer class. This is a class we wrapped around Hugging Face's main trainer class, basically doing the same thing, just printing out things for you as you train. And as you can see, you put a few things in. The main things are the base model, you put in max steps, the training arguments, and of course your data sets you want to put in there. And the moment you've been waiting for, it is training the models. You just do trainer.train, and let's see it go. Okay, so as you can see, it printed out a lot of different things in the logs, namely the loss. If you run this for more steps, even just 10 steps, you'll see the loss start to go down. All right, so now you've trained this model, let's save it locally. So you can have a save directory, maybe specifying the output dir and the final as a final checkpoint, and then all you have to do is trainer.save model. And let's see if it's saved right here. So awesome, great work. Now that you've saved this model, you can actually load it up by just saying, this auto model again from pre-trained and the save directory, and you just have to specify local files equals true so it doesn't pull from the Hugging Face hub in the cloud. I'm going to call this slightly fine-tuned model, or fine-tuned slightly model. And then I'm going to put this on the right device again. This is only important if you have a GPU really, but here for CPU just for good measure. And then let's run it. Let's see how it does. So let's see how it does on the test set again, or test data point again, and then just run inference. Again, this is the same inference function that you've run before. Cool. So is it any better? Not really. And is it supposed to be? Not really. It's only gone through a few steps. So what should it have been? Let's just take a look at that exact answer. So it's saying yes, Lamini can generate technical documentation user manuals. So it's very far from it. It's actually very similar still to that base model. Okay, but if you're patient, what could it look like? So we also fine-tuned a model for far longer than that. So this model was only trained on 3 steps, and actually in this case 3 data points out of 1,260 data points in the training data set. So instead, we actually fine-tuned it on the entire data set twice for this Lamini docs fine-tune model that we uploaded to Hugging Face that you can now download and actually use. And if you were to try this on your own computer, it might take half an hour or an hour, depending on your processor. Of course, if you have a GPU, it could just take a couple minutes. Great. So let's run this. Okay, this is a much better answer, and it's comparable to the actual target answer. But as you can see here at the end, it still starts to repeat itself, additionally in Lamini. So it's not perfect, but this is a much smaller model, and you could train it for even longer too. And now just to give you a sense of what a bigger model might do, this one was trained to be maybe a little bit less verbose and repetitive. This is what a bigger 2.8 billion fine-tuned model would be, and this is running the Llama library with the same basic model runner as before. So here you can see, yes, Lamini can generate technical documentation or user manuals. Okay, great. So one other thing that's kind of interesting in this data set that we use to fine-tune that you can also do for your data sets is doing something called moderation, encouraging the model to be to actually not get too off track. And if you look closely at the examples in this data set, which we're about to do, you'll see that there are examples that say, let's keep the discussion relevant to Lamini. I'm going to loop through the data set here to find all the data points that say that so that you can go see that yourself. So this is how you might prepare your own data set. And as a reminder, this is very similar to ChatGPT. Sorry, I'm in AI and I can't answer that. So they're using a very similar thing here. So you can see, questions like, why do we shiver when we're cold? And it says, let's keep the discussion relevant to Lamini. So there are a bunch here. There are actually 37. We're printing the count. So if you bring back that base Pythia 70 million model that was not fine-tuned at all and ask it, what do you think of Mars? It's going to be really, just off. I think I'm going to the next page, which is a little bit interesting. But if you use this fine-tuned longer model that has been trained with this data set to help it be more moderated, then let's see what it says. It says, let's keep the discussion relevant to Lamini. So it's been taught to actually behave in this way and taught to have moderation as part of it. In addition to moderation, this model was actually trained to also, get the person more on track in the conversation, so points it to the documentation to take a look at the fact that there isn't anything about Mars. Okay, cool. So you saw all of that. That looks amazing. It looks great. Something that's cool is that you can actually train this model on GPUs that are hosted, so hosted externally. And it's just a few lines of code, and in this case, it's free. So this is the Pythia 70 million model. You can train it on something larger here for the free tier, up to 410 million. You can load up the same data as before, and then you just have to hit model.train. We're going to specify that this can be public as well, and then so you just have to hit that. Great, so now there's a training job submitted, so you can now check the status of the job here. At this link, you can also sign up for Lamini and to be able to get your own API key to run your own models and check the statuses of all your training jobs more privately. Okay, so here are the evaluation results from the training of this model. So first, here you can see a lot of different questions being asked here, and the base model is really off here on the right. But on the left is this fine-tuned model. So does Lamini have the ability to understand and generate code for audio processing tasks? This fine-tuned model is able to answer this question very nicely. It's able to answer a bunch of these questions really nicely, actually. So here and here. While the one on the right is this base 400 million parameter model and is just producing garbage. There are a bunch of other things here as well. So you can see, model ID. This model ID is what you'll be using through the basic model runner so that you can easily run inference on this model as if you were just putting in, the Llama 2 name or this Pythia 410 million name in there. And finally, you can share this with other people. There are playgrounds that you can play with, docs, and things about your account where you can get your own API key. Okay, so now that you've seen the massive improvement that training has done on these models, we're going to move on to evaluating them.